welcome to our live webinar today, Building Blocks for Nanotechnology from Spark Ablation. My name is Andrei Linka. I am content creator for VS Particle, and I will co-host today's session together with our presenter, Professor Dr. Andreas Schmidt-Ott, VS Particle co-founder and Spark Ablation technology pioneer. Before we dive deep into our presentation today, I would like us to take a few minutes to go through today's agenda. We will be discussing handling questions during the presentation, webinar recording, upcoming events. I will give you some information about ways you can get in contact with us before I provide you with a short VS Particle introduction. And then we will dive deep into today's presentation, Building Blocks for Nanotechnology from Spark Ablation. The last part of our session is in charge with answering questions. We are taking questions during the webinar, and we will try to answer all of them after the presentation has ended. For the questions that remain unanswered, we will do a follow-up email after the session. You can find the chat room in your bottom right corner, the icon with the question mark. Please don't forget you are on mute during this session and you won't be able to speak. So for any feedback, comments and questions, please use the chat room. This webinar session will be recorded and we will send you a link in the coming days so you can share it with your colleagues or watch it later. For upcoming events, we have the VSPP1 nanostructure material printer, a product demo webinar, which is supposed to premiere in April. But for more information, please keep a close eye on our website and on our social media account. There are multiple ways in which you can get in contact with us. If you would like to know more about VS Particle solutions and how they can help you in speeding up your research, please check our application notes at www.vsparticle.com/applications. Or if you are interested in trying our technology in the safety of your own lab, you can do so by requesting a free demonstration via a form available at www.vsparticle.com or through email demo@vsparticle.com. For this and any other information, you can always contact our sales department, sales@vsparticle.com. VS Particle is a spin-off company of TU Delft in the Netherlands with over 20 years of experience in the synthesis of aerosols. And with the help of a young and passionate team of scientists and engineers, VSP is unlocking a whole new world of possibilities at the nanoscale. We develop and commercialize a completely new technology to automate the production of new materials, and we are key nanotechnology providers in different industries like catalysis, semicon, and health. Since 2014, we have helped scientists and industry leaders to drastically reduce the development time of new materials and products by enabling automated nanoparticle production. And here you can see a layout of our current product portfolio. Thank you for staying with me through this short introduction. I will now hand off today's presentation to Andreas Schmidt-Ott, who's going to talk about the history of spark ablation and about its many applications and advantages. And I will talk to you all, at the end of the session when we'll proceed to take your questions and Andreas will answer them. Andreas, you have the floor. Thank you.
All right. I hope you hear me. My name is Andreas Schmidt-Ott, and I will present a webinar on spark ablation for nanoparticle production. I will first tell you how it works, and then I will say what we can do with it, and I will mention some application areas. When I prepared this presentation, I became aware of the fact that I have been dealing with this subject for 45 years. So that also reminded me of my age. I'm older than 45 years. And here's a little story about how it all began. in the 1970s, research projects were launched about the properties of small particles. They were then called small particles or atomic clusters, or just clusters, and the term nanoparticles had not been coined yet. But it was clear, of course, even then, that these, if you make materials very small, the properties would change. That was known from theory, from quantum mechanics, and people were very curious about what these changes of properties would look like. And one was already thinking about possible applications. Yeah, this is actually how it all began. This was my first setup when I started my PhD thesis, and how I actually discovered spark ablation by pure coincidence. My task was, when I started my PhD thesis, to make a, let me just get a better cursor that is better visible, pointer. I think you can see this better. So the first thing I had to do is make a particle detector, and that was not so difficult. I got that done rather quickly. But I was struggling with how to make nanoparticles, because at that time there was no recipe and there was no place you could buy a nanoparticle producing machine. So what I did was, this was not my idea, but other people had already worked on it. I took a wire mounted at both ends, and if you charge a capacitor and then close this switch, then all the energy that is in the capacitor goes into the wire momentarily, and the wire explodes. So this is a wire exploding technique, which is actually still being used today to make nanoparticles. The disadvantage is, however, that it's discontinuous, of course, when the wire disintegrates into very small particles, and then you have to replace the wire. Now, one day, it didn't work. And it didn't work because there was a little connection problem of the wire, probably at one of the mountings. And so what happens then when this switch here is closed, when this contact is closed, is that the power supply keeps charging the capacitor, and every time the voltage reaches the breakdown voltage across this little gap, there is a spark. And so there are continuous sparks that we can produce with this same circuit. And that's what happened, and my particle detector detected particles. And so then I became aware that it's much easier and much better, because it's a continuous source, to use spark ablation to make nanoparticles. So this spark ablation method was discovered, was found by pure accident. And this is a little bit more in detail what it looks like. You have these two electrodes, and there are repetitive sparks between these electrodes, and every spark emits a cloud of vapor. And this cloud of vapor condenses to form first atomic clusters, and then what we call the primary particles, that grow up to a size of about 5 nanometers, and they stay nice and round because they coalesce. The melting point is much, much lower of these particles than the bulk, and that's why they stay nice and round. But when they grow still bigger, they tend to form such agglomerated structures. Now, the trick here is to make these pulses short enough, between 1 and 10 microseconds. And that causes an extremely high quenching. That means that the very high temperature of the spark, which can be 10 to 20,000 degrees C, is cooled down to room temperature practically immediately with this very high gradient marked here. And this is what it sounds like, and this is what the spark generator of the particle sounds like, and this is what it looks like. So this is the most modern spark generator on the market presently, and it has been built mainly for research purposes, and so it's very, very flexible. And you can also use different geometries of electrodes in it. For example, you can have electrodes as shown here that are hollow. So the gas comes and flows through one electrode, and then here are the sparks. So the vapor is produced here, and then the gas takes with it, flowing through the other electrode, these particles. And the size of the particles is basically controlled by the time they have to grow. Let me mention some features that actually make this method interesting. And of course, all of that I didn't know when accidentally I had sparks in my setup and found that it was a useful method. Back then, of course, I had no idea of how useful it would turn out to be. It can produce particles of high purity. It requires no precursor, as most other methods do, because it converts the material of the electrodes directly to nanoparticles. It works for any conducting or semiconducting material. And this is the most important point. It mixes materials. We can use this technology to mix materials in a very versatile manner, and I will come back to that. The particles are partially charged. That's also a very useful thing, because if they are charged, what you can do is you can, first of all, you can use an electric field to bring them to any point you want. You can apply an electrostatic force to them, and that can be very useful for building up devices out of these particles. And it can also be used to select a particle size. And in aerosols, that's very simple. You use a differential mobility analyzer when the particles are charged, and you can pick out one size. The method can be scaled up because obviously you can use 100 or 1,000 sparks instead of one spark. And impaction printing, I will also come back to that, is possible. Now again, it is an ideal tool for the size range below 20 nanometers. And this is actually the size range we were interested in from the very beginning, because this is the size range where properties are very strongly size dependent. And this is where also quantum mechanics plays a role, and this is where new properties occur, and this leads to new materials and new devices. It's actually quite interesting that it took so long. It took 45 years until we are now really very intensively looking for products that we can make with it. But this is a very rapid development occurring right now, which is actually occurring all over the world. Now, one thing we would like to do is, of course, control the size of the particles, and this is rather simple. Some time ago, we have derived a simple formula that gives us an estimate of the particle size under the condition that the particles are nicely coalesced, which they do automatically in the beginning. And if you want to avoid that these agglomerates with fractal-like structures occur, you can heat the extension of the exit tube to a certain temperature where you know that this coalescence further occurs. So if the particles are more or less spherical, you can apply this equation here to estimate the mean particle size that you get. And obviously, it's the mass production rate that in the VS particle unit you can adjust. That is important, the m dot. Obviously, it's also the flow rate that is, of course, also adjustable. And it's the effective chamber volume. Now, in the case of the hollow electrodes, the effective chamber volume after the particles have been ablated is simply the volume of that hollow electrode. So that's a very small volume, and that would be a way of producing rather small particles. Now, we always get a distribution, a size distribution shown here, and this size distribution is always log normal, and the standard deviation is always between 1.35 and 1.4. Yeah, that's the standard deviation. By the way, we developed this formula together with Ji-Cheng Feng, who is now who did his PhD thesis on the spark generation technique, and he's now professor at Shanghai Tech. You will encounter his name more often in the rest of this presentation because he did very useful things connected with spark ablation. Yeah, the question is, what is the smallest size we can actually make? If we look at this formula and you adjust these parameters to make D very small, we can actually go down to the size of atomic clusters, and the smallest size is 1 atom. And actually this little shoulder here in this mobility distribution is due to silver 2, and then comes silver 3, which is somewhat more stable, and silver 7 is also nice and stable because it's such a nice geometric form, and so on. Right now there are not really any applications of these atomic clusters, but I think there's a great potential. If you have one of these generators from VS Particle, you can use a model calculation, which is somewhat more sophisticated than this estimation formula, to see which power you have to use and which flow rate, power flow rate combination will give you a specific size. For example, this red curve refers to 4 nanometer particles. For some applications, of course, one would like to have only one size. So if this log normal distribution that you get is too broad, what you can do is you can use a differential mobility analyzer that you connect to the spark generator unit. And VS Particle is also offering such a device that is compatible with the spark generator G1. And of course, then you get particles that are all the same size as in this example here. These are 3 nanometer particles. Now let's come to my favorite topic, and that is mixing. If we want to make mixed particles, what we basically have to do is we have to mix the vapors. So we make a vapor out of a material A and a material B, and what then automatically happens if we quench as much as we do in the spark generator, we have the temperature going down to room temperature very, very quickly. That's one of the most important features of this method. Then we get more or less instantaneous formation of atomic clusters, and they grow to form our nanoparticles of any size we want. And if, for example, we take an electrode consisting of gold and the other electrode is platinum, we will then get particles that are mixed and that are a mixture between gold and platinum. Now, in the bulk, that is, in the macroscopic world, gold and platinum do not mix. They do not form an alloy. They are immiscible materials. But it has been known for quite a while that in small particles and also in thin films, the range where particles or where substances, metals can be mixed and form alloys is much broader. And so practically always, if the particles are just small enough, you can take any two materials and make mixed particles out of them. Like here with gold and platinum, we see here that this 6 nanometer particles is crystalline. It's crystalline and it's an alloy. So it's an atomic mixture. And so it becomes clear that, of course, we have an incredible amount of possibilities using this method. And we have, let's say, about 80 elements that we can choose from that work in the spark generator, most of the elements in the periodic table. So those are 80. But if you now think about possible combinations of these elements, and even with different mixing ratios, then you get an unlimited number of combinations. It's more than trillions. It's really a huge, huge number, symbolized in this drawing by these little points here. And of course, a subset of these combinations form stable particles, and we expect that we can make very, very many combinations that are very stable. And for a specific application, of course, we choose from this subset of stable ones another subset that has interesting properties for this application. And among those, we can then optimize. A very interesting class of new materials are so-called high entropy alloy nanoparticles. And you see this name of Ji-Cheng Feng occurring here again. Together with the group of Man-Soo Choi in Korea, he used spark mixing to produce nanoparticles that consist of a whole lot of different elements. And these materials are crystalline, but the distribution of the elements is disordered. And that's why they have a high entropy. They have a high degree of disorder, and the high entropy makes them stable. This is a very interesting phenomenon. It comes from the Gibbs equation, where the Gibbs free energy has a negative term with entropy in it, and the higher the entropy, the more stable the particles are. And of course, the same group in the same paper cited here already showed that an example where such a material consisting of between 5 and 10 different elements is useful for catalysis. Now, another reason why mixing is interesting is that you can adjust properties. You can tune properties by the mixture. And a nice example for that is the Plasmon resonance frequency. A metal particle consists of a crystal lattice, and there are the free electrons in that lattice, and the free electrons as a cloud, in a collective movement, can form an oscillation, and that is called a plasmon or plasma oscillation. And if this resonance frequency that they have is corresponds to the frequency of the incoming radiation, then you get resonance. And if you measure the absorption spectrum as a function of the wavelength, then you see that for a specific wavelength, the absorption is highest, and that is where this resonance occurs. That's also the phenomenon that gives a metal its color. This is here for a mixture of silver and gold mixed in a 1-to-1 ratio. And you see that the Plasmon frequency for that mixture is just between the case here for pure silver. For pure silver, the resonance would be here, and for pure gold, it would be here. And so by adjusting this ratio, of course, what you can do is you can tune the Plasmon resonance. And because mixing is easy, using the spark, you can produce particles with any Plasmon resonance that you want. It's, by the way, it's also size dependent, so you can also use size to adjust the Plasmon resonance frequency. And this has a lot of applications that I listed here, from catalysis, photovoltaic sensors, to photoelectric chemical splitting of water or CO2 reduction. And a very interesting one, which I will also refer to a little bit more in detail, is surface-enhanced Raman scattering. Now, how do we mix? We have to form this mixed with vapor in some way, and one possibility of doing that I already mentioned. That is using electrodes of two different materials, if it's just two components that we want to mix. Of course, each one of these electrodes may already be an alloy. The other possibility is that we make an alloy first, and the particles will consist of the same alloy. That's also a very important feature of the spark method. And it's due, again, to the high quenching, that the particle composition is always exactly the same as the composition of the electrodes. Now, what if the alloy does not exist in the macroscopic case? Well, what you can do then is you can make a powder, and you can mix a powder and then compact the powder and make electrodes out of this compacted powder. And that way you can then make particles, and in most cases in the nanoparticle state, the alloy will exist. So this was about atomic mixing. But what you can, of course, in an aerosol, what you can very easily do is you can mix particles coming from different sparks, consisting of different materials, and then they will, in the aerosol, they will coagulate, and they will form particles that are mixed on a nanoscale, and then you can deposit these particles onto a substrate, or you can co-deposit the particles coming from two different sparks on the same substrate. And of course, one of these sparks might already produce atomically mixed, or both of them will already be mixtures in an atomic scale. And you realize when you see this that you can use this principle to make any catalyst you want. There's a maximum freedom that you have to produce catalysts. The first spark may produce what is conventionally called the substrate of the catalyst, or the support of the catalyst, and the other one the active catalyst material. And when you deposit the particles onto a substrate, if you do that in the right way, then you have a porous material, and this porous material is then the catalyst. A specific way of mixing is coating, and this is especially interesting also for catalysts. If you already come in with one particle, called the substrate particle, which can be produced by one spark generator, and you go through the hollow electrode of a second spark generator, you can then cover these particles with the vapor coming from the second spark. And so this is the gap between the two electrodes where the spark is. And the spark moves around very quickly on this whole circle, so it's practically everywhere. And when this vapor meets the particles, the vapor molecules might have grown a little bit to form atomic clusters, but more or less they form a shell around the particles, consisting of the material of the second electrodes. And then there are several possibilities. In the case where the coating has a smaller surface free energy than the substrate, then you get a core shell particle. And more interesting for catalysts is when the coating has a higher surface free energy than the substrate. And this is what you typically have when the substrate is an oxide and the catalyst is a metal. Then you get something that we can call a decoration that you usually have for catalysts. We did this this was mainly the work of Tobias Pfeiffer, who is now the CTO of VS Particle, for a polymer. These were PSL spheres. These were the particles, and they are, of course, it's a polymer, so they are heat sensitive. And so we make use here of the fact that the vapor meets these particles at a temperature which is already near room temperature. And you see on the micrograph that they look very nice. Yes, now let me come to deposition. If you want to make a product, then you usually have to deposit the particles onto a surface. So the task is you have an aerosol coming out of the generator, and you have a substrate onto which you want to gather the particles. And you can do that basically by three different ways. One is filtration. You have a material that is usually a fibrous material, and lead the aerosol through a filter material, and then the first particles will stick in the filter material, and when you build up, then you can build up a cake on this filter material, forming a porous layer. If you want to gather only few particles, low surface coverages, and rather homogeneous coverages, you get by using diffusion. So if the aerosol is flowing here and you put a substrate into this flow, then you rely on the diffusive motion of these particles, and some of them will hit the substrate, and due to van der Waals forces, they will stick there. A third method, which is very useful, is impaction. There you have a jet carrying the particles, impinging on the substrate. And this principle is the same principle used in the printer. You can make a printer based on impaction if the substrate performs an XYZ motion, and then you can print porous layers practically in a 3D manner. So you can print any shape, a 3D shape you want, using this principle. And this is what the printer looks like. This is the so-called P1 from VS Particle. And of course, you can combine it with the other devices, with the G1 spark ablation generator and the S1, which chooses the size you want. And there are some smaller accessories that you can use by simply using diffusive capturing of the particles, or just a simple impactor, or a filter material. Let me say a little more about filtering. It's a very effective way of depositing the particles. You don't lose a single particle because they all get stuck in the filter. And you see here micrographs of a filter where only very few particles have been filtered, and here is the stage where the pores in between, the voids in between, have been filled. And after that, you get a cake formation on this filter. So this is the porous material that is caught on the filter, and you can make the layer basically as thick as you want. And it has a void fraction, which you can estimate that is around 80%. So it could almost be called an aerogel. It's a very porous material. And instead of making micrographs, you can monitor the pressure drop across this filter, and that will tell you in this bend here. You will see when this bend happens, this is the point where the cake formation starts, and the pressure drop from there will tell you how thick the layer is that has been accumulated. Yeah, this is what the printer from VS Particle looks like. Now it's writing lines. And of course, you can write anything you want. You can not restrict it to lines, but for many applications like sensors, a line is already what you want. You can, of course, use the printer also to mix materials. Here's the printer and two of the G1 units producing particles of different materials. And that way you can make a catalyst that is doped by another material. You can mix materials this way, as I explained before. These lines are broader or more narrow, as Joost van Ginkel showed, depending on the distance of the nozzle to the substrate. And here is a profile of those lines, and you can see that if the distance is 0.2 millimeters, that's the blue curve, so that's 200 microns. That's the distance. Then the width of the line is then from plus 35 to minus 35, something like that, is then around 70 microns. So with a nozzle distance of 200 microns, we get a width of about 70 microns, and the width can be increased by increasing the distance. The void fraction here is much lower than the void fraction that you get in filtering. It's about 30%. And of course, the void fraction can also be modified by modifying the conditions of the printing process. Now, here's a very interesting thing that you can get a resolution that is even smaller than 1 micron by including electrostatic forces. And so this makes use of this feature of the spark generator that many of the particles are charged. This is again Ji-Cheng Feng, mentioned for the third time in his collaboration with the Mansu Choi group in Korea, who developed this technology that they call electric field assistant aerosol lithography. You have a mask and you pre-charge that mask by ions, by putting ions on it. And that creates an electric field, and that electric field focuses a beam of particles impinging on this substrate. And that's how you can focus down to smaller than 1 micron, and you can build 3-dimensional structures with that method. Now, let me mention some applications. There's a whole lot of applications. There's a book that has been published recently with 18 authors that all have a lot of experience in spark ablation. And I don't expect you to read all these applications here, but maybe you have a chance to get the book. I will pick 3 of these applications. The first one is chemical sensors. Basically, a chemical sensor can be made very easily with a printer. You have the spark generator, and in this case, it's a metal oxide chemi-resistive gas sensor that we're making, and we can make tungsten oxide particles simply by adding a little bit of oxygen behind the spark generator, and even at room temperature, these particles react immediately because they're so small with oxygen and form WO3. And now the printer can draw a line between 2 contacts. And if you then measure the resistance between these contacts, you will see that when NO2 is added, this is an NO2 sensor, the resistance changes by 2 orders of magnitude if the concentration is 10 ppm. And so there's hardly any noise here. There's no noise, so we can go deeply into the part per billion range with this sensor principle. And of course, you can make 1 sensor, or you can make 100 sensors or 1,000 sensors and put those together in an array. And what you then have can be called an electronic nose. And things like that have already been done. I don't know if the spark generation technique has been used for it, but it would be very simple to make a sensor array using this technique. What you then need is a neural network or some very smart computer that constructs from the combination of these signals of all these sensors that all are based on a different particle material, that constructs from it a label saying this smells like gasoline or whatever. Another sensor principle, actually a colorimetric principle, is shown here. And the sensor is then actually nothing else than a coupon of some filter paper with some of our particles on it. And if there is a reaction with a specific reactant, like in this case, sulfur-containing molecules, then the color will change. So it's the color will change. You can see with your eyes, and maybe in the most primitive case, compare to a scale, or you can use an optical signal, develop an optical signal out of this color change. Basically, any mobile phone can do that, and get the red, green, and blue components of the color, and then give you a measure of the corrosiveness of ambient air, for example, with respect to silver. And that tells you if a silver object is going to tarnish or not. the tarnishing takes a couple of hours or months even, and our small particles are much, much more reactive, and so we can predict whether it will tarnish or not within minutes. Surface enhanced Raman scattering is a very, very strong method to make sensors, especially for organic molecules, and detect even single molecules if it's done in the correct way. And important for this technology is that we have plasmonic particles, and they have to have the right composition and the right size and the right structure. And of course we can do this by using spark ablation together with printing. And what happens then is that a laser beam comes into resonance with the Plasmon frequency, and if there are molecules at the surface, then exactly where these molecules are at the surface of the particles, the electric field of the radiation is amplified by a very, very high factor. And so you get a very strong signal, which more precisely is inelastic scattering. And this inelastic scattering signal forms a fingerprint. It forms a fingerprint, and this fingerprint is characteristic for the molecule. Possible applications here are medical, trace components in human breath, explosives, drugs, viruses can be detected. At least people are working on that. It's a very contemporary thing, of course. And now let me say something about catalysis. There's some nice work, among others, by Freddie Weber and his group. They used spark ablation together with a heated tube for what they call aerosol catalysis. We have an agglomeration tube following, where well-defined primary particles, particle sizes agglomerate to form these very high surface area agglomerates. And then if you add trace gases, and you can follow a catalytic reaction. In this case, they used a nickel catalyst, and they found that the turnover rate as a function of the particle size is such that in the aerosol phase, the best particle size is around something like 14 nanometers. And in the supported case, they did both. They also supported them on a substrate. The optimum size is larger. So this is a screening method, in this case used only for the particle size within the agglomerates. But of course, the same screening method could also be used for any, using different mixtures, using different components. And the fact that a nickel catalyst here is still being used for this reaction shows that this mixing hasn't hardly been used, that catalysts are still being used that consist of elements, means that the trillions of possibilities that we have in mixing have not really been used. It would be an incredible coincidence if the pure material would be better than any mixture. In the end, I would like to mention another method that is called shiners, and that has been very recently, the group of Bert Weckhausen has shown that surface enhanced Raman can be used to follow a catalytic reaction. And for that, you need these plasmonic particles on the surface. And these plasmonic particles then have to be covered by the catalyst that you want to test. It's also a screening method. And of course, you can produce these very simply with the spark generation process. And this was done by this group. These are the plasmonic particles. They are covered by a layer of silica, and the in this case 2 nanometer nickel particles have been brought to the surface by diffusion using this small diffusion sampler here. Okay, this is the last application I wanted to mention, and I will come to the conclusions that spark ablation offers great opportunities for discovery and development of new materials. I think that's quite obvious, and I showed 3 examples, including surface-enhanced Raman that can be used for very, very sensitive detection. And I expect breakthroughs to happen because of the huge possibility linked to the unlimited mixing capability that we have. Of course, particle size control is also important, and it's also important that this method is mainly interesting for the very small particles, where most of the development of the future will happen. And least not last, purity that we can offer in the gas phase is very important for many applications. So if you found this interesting, you can get many more details from 450 pages of the book that was recently published, and that I edited and wrote together with a large number of authors. Maybe you have the opportunity of borrowing it or buying it. Thank you very much for your attention.
Thank you so much, Andreas. I hope everyone found the presentation insightful. We did receive a lot of questions. Unfortunately, the time is limited, so we won't be able to answer them live today, but don't worry, we will follow up with the answers after this session. So I'm just gonna take 2 or 3 questions that can be answered in the time that's left. First question is, does this process have to be run at atmospheric pressure, or could it be performed at lower pressures? Andreas?
Yeah, well, the answer is that the pressure is in principle flexible. It is usually run at atmospheric pressure because it's just easiest to do that. But what changes when you change the pressure is the breakdown voltage. And so the distance between the electrodes will have to be different if you vary the pressure. I think the VS particle unit is designed for atmospheric pressure, but you can also use 2 bar instead of 1 bar. It will still work. If you go down to rather low pressures, then probably some modifications would have to be done in the device. But that can be discussed, of course, with the people who know more about the assembly of the generator.
Thank you, Andreas. Proceeding on to the next question. Thanks for your interesting presentation. You have mentioned a carrier gas. Is this inert? Can it be switched to another gas? Andreas?
Yes, well, usually we use inert gases because we don't want the electrodes to change chemically during the ablation process. If there are small amounts of oxygen in this gas, like in the ppm range, that usually doesn't matter. And if you want the particles to oxidize, if you want to make oxides, then it is better to mix in the oxygen after the sparking process. And in the same way, of course, you can also make sulfides and other compounds out of the particles. That is usually quite easy to do because these particles are so small and then they're very highly reactive. And usually you don't have to increase the temperature for that reaction. They react at room temperature.
Okay, thank you, Andreas. And moving on to the last question of today's session. Purity was mentioned as an important feature. Can you explain why this method has advantages with respect to other methods?
Okay. Why is the method such a pure method? Well, generally, doing particle reduction in the gas phase can be done in a much purer way than in liquid. And that has to do with the diffusion coefficient in gases. We can clean gases much better than we can clean liquids because diffusion to a getter material that collects the impurities is much faster. That's one reason. Another reason is the sticking of impurities to surfaces is usually better in the gas phase. So gases can actually be made as pure as you want. We made magnesium particles, unoxidized magnesium particles with the spark method, simply by having a lot of material present that reacts with oxygen. And you can buy such purifiers. They're on the market, and if the purifier does not purify to a sufficient degree, what you can do is use the particles themselves because they have a huge surface area, of course. So if you contaminate the whole setup from the inside with magnesium particles first and form these cakes, as I showed them, this porous material around the in the inside of the container, then there will not be a single oxygen molecule that survives, and the gas will be completely clean with respect to constituents that that are taken away by the layer formed. Was that clear enough?
I think so. Unfortunately, our guests cannot speak, but we would have gotten some comments if they didn't understand. Thank you so much, Andreas, for this very insightful presentation today.
Okay, well, thank you, Andrea.
And I would also like to thank our guests and to tell them that we will do a follow-up with the remaining answers after this session. And I expect to see you in our future online endeavors, namely the P1, the nanostructured material printer demo, which will premiere somewhere in April. Until then, I wish everyone a productive day and a nice weekend. Thank you, everyone, and talk to you soon. Bye-bye.
Bye-bye.